Up next, we have Frank Marfai. He is a mathematics faculty at Phoenix College. His work with open educational resources, as well as his work with math curriculum, spawned a collaboration, a successful collaboration, between Scottsdale Community College and Phoenix College. This collaborative team took on the task of creating or taking kinesthetic tools such as internships or fraction circles and translating those to the online environment. They also made these tools open educational resources, which is just really super cool. So let's invite Frank onto the stage.
Thank you so much. Well, welcome. It is so wonderful to be here today, and I really look forward to talking about a collaborative journey between Phoenix College Mathematics faculty and Scottsdale Community College Math and Computer Science faculty. And this is a story about the bears and the artichokes. And it includes a story about hopscotch, beanbags, and breakfast. Welcome. So what has happened is, at that time, a couple years back, the math modules were coming. And this was a curriculum that was developed as a collaborative effort among all Maricopa mathematics faculty. And so what we wanted to do is we wanted to adapt it to local needs to our college. So the curriculum, the modules curriculum, included conceptual ideas and also rigor, which basically helped connect the why and the how of mathematics. To this end, to understand the why, we use something called math manipulatives. And if you're wondering what a math manipulative is, it's basically a physical object such as this, where you can use it to teach math concepts. So here's an example of one of the math manipulatives, which was our base 10 blocks. Here we have Cuisinart rods. We also have integer chips, which is used to teach about sign numbers. And the fraction circles you just saw. And even something as humble as patty paper that you would normally think in the context of hamburgers can be used to teach mathematical concepts. All these manipulatives that we bought at our department were put into storage bins. They're about 50-pound storage bins, and then there's this massive logistical operation to put it into all the classrooms. At least I lost a few pounds doing that. So what it is as we were looking at it, we wanted to increase access to students and for faculty. So we wanted this to be an open educational resource, one. So that means it's free and reduced cost. But we also started thinking about, but wait a second, these are manipulatives you can use in class. We did have a dilemma. Our dilemma was, what about the students who were online? Or let's say those students who wanted to take it home. We couldn't do that. That was not feasible. So this created both a dilemma, but also an opportunity. Our colleagues at Scottsdale Community College, in particular William Meacham, was a computer science teacher, and we had collaborated in the past, so we decided to reach out. And we were also awarded a capacity building grant, a Title V grant at Phoenix College. And part of that we wanted to do was to adapt our OER curriculum, and we also wanted to build these virtual manipulatives because we wanted to make sure that that idea of the why math works is accessible to all students. So, over breakfast, myself, James Sousa, William Meacham, and Darren Nearing, we met and we discussed opportunities to collaborate. And there was a brainstorming of possibilities. The breakfast was also delicious. That's a bonus. But as it is we were brainstorming, then we sat back and we thought about it at our respective institutions, and we came up with the idea, let's do this amazing thing with virtual manipulatives. That's going to be amazing. It'll be free for all, centrally located for faculty and students. They can use it, and perhaps this is something that could be used at our local schools or at their state schools later on. So a proposal was made. We went through the formal process. Our administrations really said, hey, go for it, let's do it. And the collaboration between our two campuses began. So begins the story of the bears and the artichokes. So if you're wondering how this works, if you're wondering how did this collaboration work? What we did is we met every week. And for example, we these are the Cuisinart rods that you saw a little earlier. And so the idea is we had weekly meetings. The first team was myself and Bill Meacham and Mary Clements. And we were working together and thinking about how is this going to be used in class. So we brainstormed the possibilities, like this is how we would use it in class. And then what we did is we built a working prototype. So this is like a first working prototype of those Cuisinart rods. Another example is Patty paper, and as the collaboration continued, other faculty joined the team. Deborah Morian and Marcia Corby joined the team, and then we also got input from other faculty. And so we ended up with, again, there's the Patty paper that you saw a little earlier. How is it used in class, for example, to teach the concept of fractions? A lot has to do with fractions because that seems to be one that students particularly hate. And probably some of the audience members are like, nah, I don't like fractions either. So, I mean, that was one of our big focuses, like how can we make understanding fractions easier too? So as we're looking at this, this is an example of how something that was paper and pencil got virtualized, and this is an early prototype. And this is a later prototype that could be assessed, like you could actually tell if a student is doing correctly by going through the different stages of the why of mathematics. So that is something we also wanted to accomplish during this collaboration. So here's a story about hopscotch and beanbags. So I'm going to tell a little bit about the story of how these SEM virtual manipulatives came into being. So as you're looking at it, how it originally came is a colleague shared a story with me. She had a felt blanket and she was tutoring a third grade student. And the student would be throwing beanbags at the different multiples of numbers. So he'd be counting 3, 6, 9, and so on, learning the times tables. And this was so effective that the third grader's younger brother joined in the game, and his younger cousin joined in the game. And they all said, I got it, I understand what multiplication is all about. Every time you hop, there's 2 spaces, and then you get to the next multiple. So my colleague kept working with the students to the point where they just knew all their multiples. And this is a first grader said, you know what, I now understand what multiplication is all about. It's not that hard. My colleague was just reassured. She said it was gratifying to see that. So that's the story of how hopscotch, and you can see it kind of jump away, and beanbag started. So what we'll do, I'm going to show you is like how it started. So what we first did is we sketched it out. What would we want this virtual manipulative to look like? Then there's an early prototype that we're trying to do the multiples. In this case, in this screen, you're looking at all the multiples of 5 and 7. And then notice now later, you're starting to see something that looks like beanbags that you can imagine throwing onto the stage. And later, as you can see, as we worked together and we got feedback from faculty and students who were starting to test these in class, we got further refinements to this mathematical manipulative. And then later on, we also wanted to make sure that it's really accessible to all, so we also added labels all to the side, so you can actually tell what color is what. So here's an example of how this virtual manipulative actually works. We're going to actually trace right through it. So as you're looking at it, what I first want to do is, let's say I want to do the multiples of 5. So as we're doing the multiples of 5, well, you would go 5. And then later on, let's see, if we're doing 5, the next one's 10, 15, and then 20, and 25. So it's really like that beanbag experience, right? You're just throwing them onto the blanket. Oh, let's just toss them all. It's faster. And then, well, let's see, we wanted to do the multiples of 7, kind of doing the same thing. We're trying to learn our times table 7. And so you would drop a beanbag onto 7. And then we would say, well, the next one should be 14, and then after that, 21, and then 28, and then 35. And at some point, this gets redundant, so let's just throw it. And then what would happen if we go a little bit beyond this, which is, what if you were to take 5 and 7 and try to see what happens when you put both of them down simultaneously? So we'll put down 5, and then we'll put down 10, and then 15, and then 20, and then 25, and 30, and 35. Oh, and let's go to 40. Okay, now let's see what happens with 7 when you're actually doing this at the same time. So you have 7, and then you have 14 that comes soon after. And then you have 21, and then 28, and then 35. Oh, that's interesting. And then there's 42. So the first thing you'll notice that something happens at 35. There's this common multiple. Well, let's just see what happens when you throw a bunch of the tiles and see if this happens again. So we'll do that. And you'll notice that there actually are 2 common multiples. Actually, there's more if this chart were to keep going. But the common multiples are 35 and 70. The least common multiple is 35. And the idea of least common multiple is an important idea in math, especially when you're trying to add fractions. So again, this is now the story of the base 10 blocks. This is what the base 10 blocks look like. Carry it to class. Again, you lose weight. It's great. I don't recommend it, though. So one of the things is we want to see how could we virtualize this so that people could either extend these ideas from class at home, or the students who are online, we really wanted to make sure. So there was something that existed earlier in an assessment system we call Maths. which was good at representing numbers. It only could do representation of numbers. So here you have the number 132, and it's expressed as 100, and then you have 3 tens, and you also have 2 ones, which give you 100. So that's a concrete visualization of what 132 really is. So what we wanted to do is to make what you see on the left side look more like the right. So as we were collaborating together, the first thing you'll notice is that same manipulative now looks much more like what you see on the right, which is what the classroom experience would be like. And later then we built an early prototype, as you can see. We also started thinking about operations. So when we look at these operations, you'll notice that there's some red objects as well as there are blue objects. And it actually, based on what you're doing, the red objects make sense in certain contexts, like when you're doing subtraction. Today we're going to focus on the blue, because I'm going to show you a quick demo of how this works. The first thing is, let's just go and represent 132 using those base 10 blocks. So the first thing we'll do is we'll put down 100. Then we'll put down 3 tens, and then we'll also put down 2 ones. Notice how quickly that went. It's much faster than when you're doing it by hand, but another thing you'll notice is it was relatively quick. This is actually a result of feedback from students and faculty, because when we first created these manipulatives, we actually had to literally put them on to the stage, like this. And people said, well, that was kind of cumbersome. So it got much easier to use as well. So that collaboration helped make something better. Now let's take a look at another thing. Let's say we wanted to add 198 and 23. How would that look like when you're actually trying to understand the why of math? So here's your 100. Then there's going to be 9 tens, which are represented by those rods that you see there, because each one represents 10. And then we're going to put down 8 ones. And if you're thinking about adding means that you're putting together, you're combining, you're trying to figure out what the total is. So what we're going to do is put 23 down onto the stage, 2 tens, and then 3 ones as well. So as we're doing that, well, it would be really nice to combine these numbers, so why not? What do we have to lose but to combine? So let's combine the numbers. We're going to actually add the numbers together. And what you'll notice is on the right side, there's an arithmetic operation that corresponds to what's really happening. So notice now we have 11 ones. Well, let's see. 10 ones is the same as 1 10. So we recomposed it, and you'll see that now we can actually see what it does. And if we're going to add together all the tens, well, you actually end up with altogether 12 tens. But 12 tens contains 10 tens. So why don't we take that? 10 tens means the same thing as 100. We'll group that together. And it turns out that the sum of 198 and 23 is 221. You just saw it happen in front of you. So it begins to explain why things work. It's not just this process you do, but there's actually something really behind this as well. Integer Steps has another story. As you can see, I already dropped the integer chip on stage, and that's kind of the story of part of it. It's an amazing manipulative when you teach with it. But then you also end up in all these weird places on your room. Like I just tried to show the manipulative and it fell on the floor. So actually this is perfect for this example. So that was one of the issues, is the chips they get lost easily. But we, again, wanted to create something that is equitable and promotes equity and access to all students. So again, we're going to talk about the virtual manipulative. This is the first virtual manipulative that existed prior to the start of this project. And this is the number 2. So when you look at these positives, this represents 2. And then you also will notice that a negative would represent a negative 1. So a positive so there's 2 positives there, therefore that is positive 2. As we're looking at it, this is also 2. It just looks a little different. And this is going to be a fundamental idea that ends up becoming useful later. Multiple representations of the same number. So you have an additional positive and a negative. So one's a positive one and a negative one. Those neutralize, they become a 0 pair. So it's really like saying 2 plus 0, which is still equivalent to 2. It becomes an idea that you end up using in signed addition and signed subtraction. So, oops, went too far there. This is the first evolution of the virtual manipulative. It's starting to now look a little bit more like what you see here. Again, the first iteration didn't have any operations, just can we represent numbers? But later on, this first prototype, we can now start adding and subtracting signed numbers. And then with the next one, you can even do more with it. So let's take a look at what that looks like. We'll start with the humble 2, right? So again, thinking back to what's happening, the yellow is going to represent positive 1, and the negative is going to represent negative 1. As we're doing this, let's put down 2 onto the stage. That went pretty fast. If you don't like that, we can always make it this way. So it lets you move objects on the stage. But the question is, can we represent 2 multiple ways? Well, that is a 0 pair, So this because there's a positive one, negative one. So it's effectively like 2 plus 0. Well, why stop there? Let's put another. 2 plus 0 plus 0. 2 plus 0 plus 0 plus 0. Oh, what the heck? Let's throw another one on. 2 plus 0 plus 0 plus 0 plus 0. Okay, well, this is awesome and neat, but is it really the same thing as 2? Well, let's see. If we take a negative and positive, that's 0. Negative and positive, that's still 0. So that's still 0, and that's still 0, so you still really have 2. It was just 2 in disguise. Let's start over. Now, you might wonder why this was useful. Let's say I wanted to take 2, and I want to subtract 5 from it. That doesn't sound right. If we are thinking of this as chips, concrete objects, 2 subtract 5 means we want to take 5 yellow chips away from the stage. We don't have 5 yellow chips, but we have a solution. Well, that's still 2. 2 plus 0 plus 0. 2 plus 0 plus 0, it's still 2, but we now have a dilemma that's been resolved. We now have 5 yellow chips on the stage. So as you're looking at it, guess what? We can remove 5 yellow chips. So 2 minus 5 is negative 3. If I have $2 and I spend 5, I am $3 in the red. So what you can see here is that this actually shows why things work. There is an actual logical meaning behind why 2 subtract 5 is negative 3. Our last one here is fraction circles, because I thought I'd promise. Well, I brought the prop, I might as well show this thing, right? So as we're looking at this, one of the things you'll be noticing is that fraction circles are awesome. I love these. I also hate taking them out of my room or putting them out. If you ever teach with this, these are amazing. They also take 10 minutes to put out and 10 minutes to put away. Okay, so how much class does that leave you, really? If you lose them, it's a game of 51 pickup, not 52 pickup. Because I've dropped them once, it's not fun. So actually, the virtual manipulatives help also enhance our learning opportunities, not only outside of class, but inside of class. So we would start with, again, an original prototype, and then notice it got a little bit more sophisticated. We have different drop zones. And then we started thinking about, well, what about mobile? We were developing a lot of these early ones on computer, but what about students who use tablets? Or what about students who use their phones? We wanted to stay current, and so what we did is we redesigned it so it's now mobile friendly too. And then later on, we took information from the pilot. And you said, this is such an awesome thing, everyone's gonna love it. No, that's not true. So it turned out, as we were getting feedback from our initial pilots, some students didn't care for it. And we tried to actually dig down deeper, why is that the case? And it turns out that some of those students who really didn't care for it had color blindness. So the question is, this produced an interesting dilemma, but we also wanted to make sure that this is really a tool that's useful for everyone. So to understand that better, 8.5% of the population have some form of color blindness, some variation of color blindness. And so what I would do is, if you were trying to look at through the world through their eyes, well, we were able to simulate what that looks like. So these are different variations of color blindness. And one of the things I want you to notice is, can you tell the fraction circles apart so easily during these different variations of color blindness? Like this last one. It became hard to tell what is what. So what we did is we went back and we redesigned each one of those manipulatives so that if you look carefully, you can see the label on each. So a little demonstration of how this actually would work. Let's say you want to see the fraction that's equivalent to 1/2. So the first thing we're going to do is we're going to put on stage 1/2. And let's say we wanted to represent 1/2 multiple ways. Let each circle represent one whole. So the first thing we'll do is just put all the halves. We're guaranteed that each one of them has a half in it, so far this is good. But what you can do with a manipulative is that you can either choose to be opaque or transparent when you do the manipulatives. So as we're looking at this, let's just see what else we can do. So what we're going to do is, okay, that's 1/3, this is 1/4. Let's put down 1/4. So that's our first fourth, and this is our second fourth. So 2/4 is equivalent to 1/2 because it covers the same portion of a circle. And if we were to look at some others, we could also see the same with that is a 1/6 slice, which is teal. And you'll notice that is a 1/6, 2/6, 3/6. And that 3/6 is also equivalent to 1/2. And so lastly, what we're going to look at is over here, when you're looking at this, 4/8 is also equal to 1/2. That tells us that 4/8, 3/6, and 2/4 is the same thing as 1/2. So we actually found 3 different fractions, but there may be others as well if you were to explore the manipulative as well. So what did we want with this? We wanted an OER resource for students. These are some of my students who are pre-service teachers who are actually using the virtual manipulatives in my class. They're going to be in the classroom in a couple of years. And there are students in developmental math courses that are also using this as well. You notice one of my students is using a laptop, and you also notice my other student who is in the back she's using a tablet to explore these ideas of virtual manipulatives. So think about this, is that these future teachers will be using these type of resources in their classroom. And so this is an OER resource for students and faculty. I showed you a couple of what they look like. Encourage you to explore if you're interested. It's free, and it always will be free. That's why we want it to be OER. And so I wanted to again thank everyone who has contributed to making this process possible, faculty, staff, and the administration of both Phoenix College and Scottsdale Community College. We were to do amazing things together that we were not able to do together, or we would not have been able to do alone. So it's a wonderful journey, and thank you all for coming today.
Thank you, Frank. Did you enjoy that? Does it make you want to take a math class from Frank? Yeah? Play around with those colors, you know? If I'd had fractions like that when I was in school, it would have been a whole different ballgame.